Welcome to this gentle exploration of the universe's most magnificent forces, where celestial bodies dance through the cosmos in patterns so precise they've inspired poets and guided civilizations for millennia. Tonight, we drift into the story of gravity and magnetism, those invisible choreographers that shape everything from falling raindrops to spiraling galaxies, orchestrating a ballet that has played without pause for nearly 14 billion years. As you settle into this quiet moment, perhaps you're watching the evening sky deepen into darkness, or maybe you're listening during a peaceful afternoon break. Wherever you find yourself, know that you're witnessing this artistry in every moment. The gentle pull that keeps you grounded, the moon's slow arc across the heavens, the very breath flowing through your lungs, all participate in this cosmic dance that connects every grain of sand to every distant star. If you find comfort in these soft-spoken journeys through science, I invite you to subscribe. How is your day? Wherever you are in the world, whatever time it is, I'm really glad you're here. If you feel like it, comment your time and location below. It's always amazing to see how far and wide we're connected, even as we wind down together. Tonight, we begin our story not with equations or complex theories, but with a simple truth that would have astonished our ancestors. Right now, as you rest in the comfort of your surroundings, you are traveling through space at extraordinary speeds. Earth spins on its axis at over 1,600 kilometers per hour, while simultaneously racing around the sun at 30 kilometers per second. Our entire solar system sweeps through the Milky Way at 220 kilometers per second, and our galaxy itself drifts through the cosmic web at an astonishing 600 kilometers per second. Yet you feel perfectly still, cradled in gravity's gentle, unyielding embrace. This is the profound elegance of our cosmic dance, so vast and so smooth that we experience only a sense of peace within its rhythm. But how did this magnificent choreography begin, and what invisible hand guides the steps of planets, moons, and stars as they waltz through the endless night? The story begins with gravity, the oldest and most patient of the universe's great forces. It is a fundamental property of matter and energy itself, a subtle curvature in the very fabric of space-time. It does not pull in the way a rope does. Rather, it tells planets how to move through a universe that has been shaped by the presence of mass. It is a whisper that commands galaxies, a silent conductor for a performance of impossible scale and beauty. The story unfolds in the early universe, a time almost beyond our imagining, when all of space was a searing, incandescent fog, denser and hotter than the heart of any star we see today. In those first moments after the Big Bang, the cosmos was a place of almost perfect uniformity, a smooth, featureless expanse of energy and nascent matter. But the universe was born from the realm of the quantum, a world governed by uncertainty, and so it could not be truly perfect. Tiny, fleeting quantum fluctuations, whispers of possibility at the smallest conceivable scales, rippled through the fabric of space-time. Then, in a fraction of a second, a period of astonishing expansion called cosmic inflation stretched the universe exponentially, taking these microscopic ripples and magnifying them to astronomical proportions, seeding the cosmos with the almost imperceptible variations in density that would serve as the blueprints for everything to come. Into this nearly uniform cosmos, gravity began its patient, inexorable work. The process was unthinkably slow, a silent, gravitational tide playing out over millions of years. Where matter and energy were even slightly denser, gravity's gentle pull grew infinitesimally stronger, beginning to attract more material from the surrounding regions in a cosmic, rich-get-richer scheme. Where matter was slightly less dense, it became even more rarefied as its contents were slowly but surely drawn away, drifting toward the growing gravitational wells. This was not a violent or sudden act, but the most patient and persistent of sculptures, as gravity began to slowly etch the first faint lines of structure into the smooth canvas of the young universe. transforming a featureless expanse into a landscape of subtle hills and valleys in the gravitational field. But this grand construction had an unseen architect, a mysterious substance that outweighs all the stars and galaxies we can see by more than 5 to 1. Dark matter. This ghostly substance, which feels the pull of gravity but does not interact with light or any other form of electromagnetic radiation, held a crucial advantage in the early universe. While ordinary matter, the protons and electrons that would one day form us, was trapped in a hot, glowing plasma, pushed and pulled by the intense radiation of the cosmic dawn, dark matter was immune. It felt only gravity, and so it could begin to clump and collapse into vast, invisible halos long before ordinary matter could. It formed a silent, invisible scaffolding, a ghostly architecture of immense filaments and concentrated nodes, tracing the lines of those initial quantum fluctuations. Then, after 380, 0, 0, 0 years, when the universe finally cooled enough for atoms to form, the stage was set. Ordinary matter, now free from the tyranny of light, was finally able to answer gravity's call. It fell like cosmic rain into the immense, pre-existing structures that dark matter had already built. The gas of the cosmos flowed in great rivers toward the densest parts of the invisible web, leaving behind vast, empty voids that grew ever larger and more silent. Over hundreds of millions of years, this process transformed the universe into the magnificent cosmic web we observe today, a luminous, web-like pattern on the largest scales, with dense filaments of galaxies stretching between massive clusters, all connected by vast, relatively empty voids. This cosmic tapestry, the largest scale structure in the universe, is a testament to gravity's profound ability to organize matter across distances so vast that light itself takes billions of years to cross them. A magnificent structure built from the faintest whispers of the universe's first breath, the first stars ignited in this slowly evolving landscape, born from the gravitational collapse of vast clouds of hydrogen and helium. These stellar nurseries were not randomly scattered, but followed the invisible threads of dark matter that had begun to define the universe's architecture. Congregating at the dense intersections of the great cosmic web, these primordial clouds were truly colossal, spanning light years and containing the mass of hundreds of thousands of suns. Yet they were incredibly diffuse, far less dense than any vacuum we could create on Earth. For millions of years, they simply drifted in the cosmic dark, their atoms moving slowly in the cold. But gravity, ever patient, was at work. It began a slow, gravitational inhalation, a gentle but relentless pull that drew the cloud inward, ever so slightly, century after century. As the cloud contracted, its density began to climb in the center, and with that density came pressure, and with that pressure came heat. A dense, glowing heart began to form, a protostar, not yet a true star, but a cosmic furnace in the making, its warmth a faint promise against the cold, empty void. Then, after an immense and silent gestation, a threshold was crossed deep within the core of the protostar. The pressure and temperature became so extreme, reaching millions of degrees, that the very atoms of hydrogen were crushed together with a force that overcame their natural repulsion. Nuclear fusion began. In a silent, sustained detonation that would last for millions of years, the star ignited. A light never before seen, the very first starlight, blazed out into the pristine darkness of a universe that had, until that moment, been entirely unlit. These were not gentle yellow dwarfs like our sun. They were blue-white behemoths, titans hundreds of times more massive, burning with a ferocious intensity that made them 1,000,000 times more luminous. Their surfaces seethed at temperatures of tens of thousands of degrees, pouring out a torrent of high-energy ultraviolet radiation that would begin to ionize and reshape the very gas from which they had been born. But these magnificent, pioneering stars lived lives that were as brief as they were brilliant. Their immense mass, the very thing that made them so luminous, also caused them to burn through their nuclear fuel at a furious, unsustainable rate. After just a few million years, a mere cosmic heartbeat, their cores collapsed under their own tremendous weight. This collapse triggered a final, incandescent act of self-destruction, a supernova explosion of a scale and violence that dwarfs any stellar death we witness today. In this final, fiery cataclysm, the stars forged in their cores and then scattered across the cosmos the first heavy elements: carbon, the scaffold of life; oxygen, the breath of worlds; silicon, the heart of rock and sand; iron, the core of planets and the salt in our blood. All the ingredients necessary for rocky worlds, for complex chemistry, and ultimately for us, were seeded into the surrounding gas clouds by these explosive deaths. Gravity, the great gatherer, had created the first stars, and those stars, in their dying moments, had given gravity the raw materials it needed to begin the next, the more intricate act of its cosmic ballet, building the worlds that would one day have someone to watch the stars. The formation of our own solar system exemplifies this cosmic choreography on a more intimate, and for us, more personal scale. Nearly 5 billion years ago, within a cold, dark, and slowly rotating corner of the Milky Way, a vast and serene cloud of interstellar gas and dust hung suspended in the void, a silent promise of worlds yet to come. This was not merely a cloud of primordial hydrogen. It was a rich inheritance, a nebula seeded with the ashes of countless generations of stellar evolution that had lived and died before it. It was a repository of stardust, containing within its swirling tendrils the carbon, oxygen, and iron forged in the hearts of those long-dead stellar titans. For an immeasurable time, it drifted in a state of delicate equilibrium, its own faint gravity pulling inward, perfectly balanced by the gentle outward pressure of its gas. But this cosmic peace was not destined to last. A shockwave, perhaps from the explosive death of a nearby massive star, a supernova that blazed with the light of 1 billion suns for a few brilliant weeks, rippled through the nebula. This celestial concussion disturbed the cloud's fragile balance, compressing regions within it and giving gravity the advantage it needed to begin its patient, final work. The great cloud began to collapse, not in a sudden rush, but in a slow, inexorable fall inward that would span 100,000 years, a silent, gravitational sigh, as the raw materials of our future home began their long journey toward the center. As the collapsing cloud of gas and dust drew inward, a fundamental law of physics began to assert its elegant and transformative power: the conservation of angular momentum. It is the same principle that causes a figure skater to spin faster when they pull their arms inward, concentrating their mass closer to their axis of rotation. The nebula, with its faint initial spin, began to turn faster and faster as gravity pulled it into a smaller and smaller volume. This accelerating rotation had a profound and beautiful effect, transforming the chaotic, three-dimensional cloud into an ordered, flattened, spinning structure, the protoplanetary disk. At the heart of this spinning vortex, where the vast majority of the nebula's material had gathered, the pressure and temperature skyrocketed, giving birth to a glowing, incandescent protostar, our young sun, not yet shining with the fire of fusion, but already the gravitational anchor of the nascent system. Surrounding it, stretching out for billions of kilometers, was a vast, thin platter of the remaining dust and gas, a cosmic potter's wheel upon which all the future planets, moons, and asteroids would be sculpted. This disk was not uniform. It was a place of gradients, hotter near the center and colder in its distant reaches, a feature that would dictate the very character of the worlds that formed within it. Within this spinning, stratified disk, in the cold and silent darkness, far from the central protostar's glow, gravity began to play its most delicate and patient game, building worlds from almost nothing. The process was surprisingly gentle at first, a cosmic lullaby, sung in near silence. Microscopic grains of dust, no larger than particles of smoke and coated in a thin frost of ice, began to encounter each other as they orbited the young sun. Initially, gravity was too weak to have any effect on them. Instead, they clung together through simple electrostatic forces, the same gentle crackle that makes a balloon stick to a wall or dust bunnies form under a bed. Over thousands upon thousands of years, these growing fluffy aggregates, like cosmic snowflakes, gently collided and merged, building up from dust to pebbles, from pebbles to boulders. As these objects grew larger, their own modest gravitational pull began to assist in their construction, attracting smaller particles and other growing clumps. This gravitational choreography, this intricate ballet conducted by Jupiter, extends far beyond the familiar confines of our solar system. For our home, this collection of planets and their conductor is itself just a single, sparkling note in a composition of truly galactic proportions. As we drift further from the comforting anchor of our sun, our perspective expands, pulling back until our entire solar system shrinks to a pinprick of light, lost in a swirling, a luminous river of 100 billion other stars. This is our home galaxy, the Milky Way, a breathtaking spiral of incandescent gas, dark, weaving dust lanes, and countless suns, all bound together in a single, colossal, rotating structure. From this imagined vantage point, floating in the intergalactic void, we would see its true form, a vast, flattened disk more than 100,000 light-years across, with graceful, sweeping arms coiling out from a brilliant, glowing central hub. It is a celestial city of impossible scale, a metropolis of stars, and like any great city, it is not static. It is alive with motion, a great wheel turning slowly and silently in the cosmic night, carrying us and everything we have ever known on a journey of unimaginable length and duration. Our sun, and our entire solar system with it, participates in this grand rotation, endlessly circling the galaxy's distant center. We are passengers on a cosmic carousel, spinning through the void at a speed that renders all earthly comparisons inadequate, a staggering 220 kilometers every single second. Yet, just as Earth's own furious motion is imperceptible to us, this galactic journey is so vast, so smooth, and so perfectly orchestrated by gravity that we feel not a hint of its true velocity. A single lap around this cosmic circuit, a journey so long we call it a galactic year, takes 250 million of our earthly years to complete. This is a timescale that humbles all of human history. The last time our solar system was in this same region of the galaxy, the first dinosaurs were just beginning to walk the Earth, and the continents were arranged in the unfamiliar pattern of the supercontinent Pangaea. Since the first complex, multicellular life emerged from the oceans, our world has completed less than 3 full orbits around our galaxy's heart. We are children of a single galactic autumn, our entire existence as a species playing out in a fraction of one celestial season. But what guides this great wheel? What is the silent, invisible axle around which 100 billion stars revolve in their patient, stately procession? At the very heart of our galaxy, hidden from our direct view by thick clouds of interstellar dust and gas, lies a gravitational entity of almost mythical power, a supermassive black hole. This is Sagittarius A*, an object so dense and so gravitationally dominant that it warps the very fabric of space-time around it into a cosmic whirlpool. It is the galaxy's unseen heart, a silent, dark anchor containing the mass of more than 4 million suns, all compressed into a volume smaller than the orbit of Mercury. While it does not suck in the galaxy as a vacuum cleaner might, its immense gravity provides the central focal point for the entire galactic structure, the still point around which the great wheel turns. For the stars unfortunate enough to live in the chaotic downtown of the galactic center, life is a frantic and perilous dance. Astronomers have watched for decades as stars like one named S2 whip around Sagittarius A times at incredible speeds, completing their tight, elliptical orbits in just 16 years, reaching velocities of thousands of kilometers per second as they make their closest approach. But we, in our quiet suburban spiral arm, are a comfortable 26,000 light-years away from this central frenzy. Our orbit is a serene and gentle one, a slow, safe passage through the galaxy's habitable zone, far from the intense radiation and gravitational chaos of the core, allowing for the long, uninterrupted eons necessary for a planet to cool, for oceans to form, and for life to slowly, patiently, and tenaciously take hold. The galaxy, then, is not just a collection of stars. It is a living, breathing, self-contained ecosystem, a celestial city with its own distinct neighborhoods, all governed by the invisible laws of gravity. There is the chaotic, incandescent, and densely populated core, a place of extreme energies and ancient stars. There are the bustling, vibrant spiral arms, the galactic suburbs where we reside, rich with the gas and dust that serve as the nurseries for new generations of stars, places of constant birth and renewal. And surrounding it all is the galactic halo, a vast, ghostly sphere of ancient, scattered stars and mysterious dark matter, the city's old, quiet, and sprawling countryside. Each part plays its role, and each star, including our own, follows its ordained path in this grand, rotating structure. As you drift deeper into this cosmic reverie, remember that you are not separate from this grand choreography, but are woven into its very fabric. You are a citizen of this star city, a passenger on a cosmic vessel of unimaginable scale, held in place by the same gentle, persistent force that keeps your feet planted firmly on the ground. The dance is eternal, and the Milky Way is the grand ballroom upon which it unfolds. But even our entire galaxy, this magnificent cosmic city we call home, is not immune to gravity's greater, grander choreography. We are not an isolated island of stars, but a part of a much larger, gravitationally bound family known as the local group. This cosmic dance troupe, a collection of more than 50 galaxies, from brilliant spirals to small, faint dwarfs, is all held together by their mutual gravitational attraction, stretching across millions of light-years. Each galaxy, a soloist in its own right, feels the subtle, persistent pull of its neighbors, and in this slow, majestic waltz, their destinies are intertwined. The largest and most luminous member of this local group, and our primary dance partner, is the Andromeda Galaxy, a breathtaking celestial twin to our own. Located a staggering 2.5 million light-years away, it appears in our night sky as a faint, ethereal smudge of light, barely visible to the naked eye under perfect conditions. Yet through powerful telescopes, we can resolve its majestic spiral arms, filled with hundreds of billions of suns, stretching out across the void, mirroring the very structure of our own Milky Way. Andromeda is even larger than our galaxy, a more massive and gravitationally dominant partner in this cosmic pas de deux. And despite the enormous, almost incomprehensible distance that separates us, gravity, the patient and tireless orchestrator, is slowly but inexorably pulling our two galaxies together. It is a cosmic embrace that has been unfolding for billions of years, a future collision that has been predestined since the earliest moments of the universe, in approximately 4.5 billion years, a time so far in the future that our own sun will have already swollen into a red giant. The Milky Way and Andromeda will merge. But this will not be a violent, destructive impact in the way we might imagine two cars colliding. Stars are, after all, incredibly tiny points of light, separated by unimaginable gulfs of empty space. The average distance between stars in our galaxy is so vast that if the sun were the size of an orange in New York City, the nearest star, Proxima Centauri, would be another orange in San Francisco. So, when our galaxies meet, individual stars will almost certainly not collide. Instead, this will be a slow-motion collision, a graceful gravitational ballet unfolding over hundreds of millions of years, a reweaving of cosmic fabric on a scale that beggars belief. As the two immense dark matter halos, those invisible gravitational anchors that hold each galaxy together, begin to interpenetrate and entangle, their mutual pull will distort the delicate spiral arms of both galaxies. Gas clouds will be compressed, igniting furious bursts of star formation, painting the newly forming galaxy with brilliant knots of blue-white light. Stars will be flung from their original orbits, like beads scattered from a broken necklace, some to new, distant paths within the merged behemoth, others perhaps to be ejected into the lonely, cold darkness of intergalactic space. From the perspective of a planet orbiting a star within this merging chaos, the night sky would transform dramatically, filled with a growing, shimmering spiral that eventually swallows the entire horizon, a majestic, terrifying spectacle that would redefine what night even means. Ultimately, after hundreds of millions of years of this intricate, gravitational mingling, the two spiral structures will blend and settle into a new, more stable configuration. The delicate, spinning disks and graceful arms will be replaced by a single, larger, and more spheroidal elliptical galaxy. This new entity, perhaps affectionately nicknamed Milkomeda by the distant descendants of humanity, will shine with a different kind of glory, a vast, rounded cosmic island with older, redder stars. This is gravity's ultimate act of creation on the grandest scale, turning two into one, reshaping galactic identities through an inevitable, patient, and truly magnificent transformation. Yet, even this merged titan, this future, Milkomeda, will not be alone. The local group itself is part of an even larger gravitational assembly called the Virgo supercluster, which contains thousands of galaxies spread across roughly 100 million light-years. And this supercluster, in turn, is just one of countless such structures scattered throughout the observable universe. Each one is held together by the persistent, patient pull of gravity, forming a web-like pattern on the largest scales, with dense filaments of galaxies connected by vast, relatively empty voids. This cosmic web represents the largest scale structure in the universe, a testament to gravity's ability to organize matter across distances so vast that light itself takes billions of years to cross them. The inevitable embrace of the Milky Way and Andromeda is but one more movement in this unending, grand ballet, a testament to the enduring power of the invisible choreographer that binds all things. As we drift deeper into our cosmic reverie, carried along by gravity's eternal, galaxy-spanning embrace, our focus now gently narrows, turning from the vast and distant to the intimate and immediate. We find ourselves drawn toward a new chapter in the universe's story, a place where gravity's role shifts from the grand choreographer of celestial ballets to the focused and powerful blacksmith of our own existence. We turn our attention to the heart of our own solar system, to that brilliant, life-giving beacon we call the sun. The same gravitational forces that choreograph the waltz of planets and bind galaxies in their stately procession also govern the life and death of our own star. And it is here, in this stellar forge, 93 million miles away, that we encounter the raw, elemental power of gravity, not as a gentle guide, but as a force of immense, creative compression, a celestial hammer that forges light and life from the simplest of materials. It is within the sun that gravity's true, transformative magic is revealed, a magic that powers our world and ultimately makes our own quiet contemplation of the cosmos possible. Picture, if you will, the sun not as the steady, unchanging, golden disk it appears to be from our serene vantage point on Earth, but as a dynamic, breathing, and almost terrifyingly violent entity. It is a massive ball of incandescent gas, a sphere so colossal it contains more than 99.8% of all the matter in our entire solar system. Its surface, that seemingly smooth golden disk, is actually a churning, boiling ocean of superheated gas, a roiling cauldron of energy where colossal plumes of matter rise and fall in convective patterns larger than our entire planet. But the true miracle, the source of all its power, lies hidden deep within its core, a place of unimaginable extremes, a realm where the conditions are so hostile that they defy all earthly comparison. It is here, in this central furnace, that gravity, the great gatherer of matter, plays its ultimate and most profound role. The sheer, crushing weight of the sun's own outer layers, a mass of 333,000 Earths, all pressing inward, generates a pressure at the core that is 250 billion times greater than the atmospheric pressure at sea level on Earth. It is a pressure so immense that it warps the very nature of matter itself. In this crucible of impossible pressure, the temperature soars to a staggering 15 million degrees Celsius, 25 times hotter than the sun's already blistering surface. This is no gentle campfire burning in the cosmic darkness, but a nuclear furnace of unimaginable power. And in this furnace, gravity's immense, compressive force brings about the most fundamental of all cosmic transformations, nuclear fusion. Here, the most common element in the universe, hydrogen, the very atoms from which the sun was born, are stripped of their electrons, and their bare protons are slammed together with a force so great that it overcomes their natural, powerful electromagnetic repulsion. 4 hydrogen nuclei are fused into a single, slightly less massive helium nucleus. The tiny fraction of mass that is lost in this transaction, a difference so small it seems insignificant, is not truly lost. It is converted directly into a torrent of pure energy. According to Einstein's famous and elegant equation, E equals mc squared. This is the secret of the stars, the source of their brilliant, enduring light. Every single second, the sun's core fuses about 600 million tons of hydrogen into helium, and in doing so, it converts 4 million tons of its own matter into the raw energy of light and heat, a sustained, silent, and continent-sized nuclear detonation that has been blazing without pause for 4.5 billion years. The energy born in this gravitational crucible, in the form of high-energy gamma rays, does not simply fly straight out of the sun. The solar interior is so incredibly dense that a single photon, a particle of light, begins an epic and tortuous journey, a cosmic pinball game that can last for hundreds of thousands of years. It is absorbed by one atom and then re-emitted in a random direction, only to be absorbed and re-emitted again, countless trillions of times, slowly staggering its way from the core towards the surface. By the time this energy finally reaches the sun's visible surface, the photosphere, it has been transformed from deadly gamma rays into the gentle, life-giving spectrum of visible light and heat that streams across the solar system. This is the light that warms our faces, the energy that powers photosynthesis, drives our weather, and makes life on Earth possible. Every ray of sunshine that touches your skin began its journey hundreds of thousands of years ago in a gravitational furnace of unimaginable power, a testament to the fact that the same force that gently holds you in your chair can, on a stellar scale, ignite a fire that can illuminate and sustain an entire world. The sun is gravity's ultimate masterpiece, a perfectly balanced and self-regulating engine, a star forged and sustained by the very force that it, in turn, uses to conduct the dance of its own planetary family. As we drift deeper into this solar story, we find ourselves drawn toward the sun's restless and elemental nature, where beneath that seemingly steady golden surface lies a world of constant motion and a state of matter so exotic and so fundamental to the cosmos that it challenges our everyday, earthbound intuition. The sun you see each morning, that familiar disk of light rising over the horizon, is not a solid sphere, nor is it a ball of liquid or gas in the way we typically understand those terms. It is composed entirely of something far more energetic and dynamic: plasma. Now, you might wonder what exactly plasma is, and it's a fair and important question to ponder as you settle into a state of deeper comfort and relaxation. We are taught in school about the three states of matter: solid, liquid, and gas. A block of ice, a solid; when heated, melts into water, a liquid. When heated further, it boils into steam, a gas. But what happens if you continue to heat that gas, making it hotter and hotter and hotter still? At extreme temperatures, the very atoms themselves begin to break apart. The intense heat provides so much energy that the electrons, which normally orbit the nucleus of an atom in neat, defined shells, are stripped away entirely, leaving behind a turbulent, electrically charged soup of free-floating electrons and positively charged atomic nuclei, or ions. This is plasma, often called the fourth state of matter, and it is, by an enormous margin, the most common state of matter in the entire universe. Nearly all the visible matter you see in the night sky, every star, every glowing nebula, the vast, tenuous gas that fills the space between galaxies, exists in this plasma state. Here on our cool, gentle, and relatively placid little Earth, we rarely encounter it in its natural form, except in the fleeting, jagged brilliance of a lightning bolt, the shimmering, ethereal curtains of the aurora, or the gentle, contained glow of a neon sign. The sun is a perfect, colossal sphere of this plasma, a self-contained world where the rules are dictated not just by gravity and temperature, but by the powerful and often bewildering forces of electromagnetism. Because plasma is made of charged particles, it responds to magnetic and electric fields with an intimacy and complexity that ordinary gas does not. It can be shaped, channeled, and constrained by magnetic fields, flowing along invisible lines of force like water in a riverbed. It can also generate its own magnetic fields as it moves, creating a dynamic, self-perpetuating feedback loop that is the key to understanding the sun's most spectacular and violent behaviors. The very fusion that powers the sun, occurring deep within its core, is a process that can only happen in a plasma state, where the bare nuclei of atoms can be forced close enough together to merge. But it is in the vast region surrounding the core, the convection zone, where the true nature of this solar plasma becomes most apparent and most consequential for us. Here, great blobs of hot plasma, heated from below by the energy of the core, rise toward the surface, much like the churning water in a boiling pot. As they reach the surface, they cool, release their light and heat into space, and then sink back down into the depths to be reheated, in a constant, rolling, convective cycle. It is this churning motion of electrically charged plasma, a colossal, slow-motion boiling that covers the entire star, that acts as the engine for the sun's magnetic field. This is the dynamo, the power plant that transforms the star's thermal and kinetic energy into the vast and complex magnetic architecture that we will soon explore. The surface of the sun that we see, the photosphere, is the visible boundary of this plasma ocean. The granulated pattern you can observe in high-resolution solar images, a texture like the surface of a pot of simmering rice, is the very top of these convective cells. Each granule is a plume of hot, rising plasma, some 1,000 kilometers across, that shines brightly for a few minutes before cooling and sinking back down along the darker lanes that separate them. This is the true face of our star, not a smooth, featureless ball of light, but a dynamic, textured, and constantly changing surface, a direct visual manifestation of the plasma physics that governs its existence. And it is this plasma, this fourth and most cosmic state of matter, that holds the key to unlocking the sun's greatest mysteries. It is the medium through which the sun's energy is transported, the source of its magnetic personality, and the very substance that it sometimes hurls across the solar system in the magnificent and powerful eruptions we call solar flares. Understanding plasma is the first step toward understanding that the sun is not just a gravitational anchor, but an electromagnetic engine of immense and captivating complexity. As you continue to relax, imagine this swirling, superheated state of matter, a substance that is both the most common and, to us on Earth, the most alien of materials, a cosmic fire that is not just the setting for our solar story, but in many ways, its most important and most active character. As we continue our gentle journey into the heart of the sun, we now turn from the substance of our star, its exotic plasma, to the invisible and powerful force that animates it. For while gravity provides the immense, crushing pressure needed to hold the sun together and ignite its nuclear furnace, there is another, more mercurial force at play, a force that gives the sun its dynamic and often tempestuous personality. This is the force of magnetism. Deep within the sun's churning, convective interior, a process of breathtaking elegance and complexity is constantly at work, a celestial engine that generates a magnetic field of a scale and power that dwarfs any magnet we could ever conceive of on Earth. This is the solar dynamo, the invisible heart that drives the sun's activity, and its rhythms and pulses are felt across the entire solar system, shaping the very environment in which our planet exists and travels. To understand this magnetic dynamo, we must once again return to that roiling, superheated soup of charged particles, the plasma that makes up the sun's outer layers. Imagine, if you will, the sun's magnetic field as an invisible, elastic web of force lines that extend from its interior far out into space, creating what scientists call the heliosphere, a vast bubble of magnetic influence that encompasses our entire solar system. This is the sun's domain. The process of generating this colossal magnetic field begins with a simple seed. The sun, like many stars, likely inherited a weak magnetic field from the very interstellar gas cloud from which it was born. But it is the sun's own motion, its complex and multi-layered rotation, that amplifies this seed field into the powerhouse we observe today. The key to this amplification lies in a phenomenon known as differential rotation. The sun does not rotate as a solid body like a spinning billiard ball. Instead, its equator spins significantly faster than its poles. A point on the solar equator completes one full rotation in about 25 Earth days, while the polar regions, moving more leisurely, can take as long as 35 days. This differential rotation, this constant shearing motion between the fast-spinning equator and the slow-spinning poles, has a profound and transformative effect on the magnetic field lines that are embedded within the plasma. Imagine a set of magnetic field lines running neatly from the sun's north pole to its south pole, like the lines of longitude on a globe. As the equator races ahead of the poles, it drags these field lines with it, stretching and wrapping them horizontally around the sun. Over time, this process is like winding a cosmic rubber band, twisting the initially simple north-south field into a powerful, tightly coiled, east-west, or toroidal magnetic field, which grows stronger and stronger with each solar rotation. But this is only half of the dynamo's magic. The second crucial ingredient is the convection, the boiling, churning motion of the plasma itself. As those great plumes of hot plasma rise from the deep interior toward the surface, they carry a portion of this strong, toroidal magnetic field with them. However, because of the sun's rotation, these rising plumes are also twisted by the Coriolis effect, the same force that creates the swirling patterns of hurricanes on Earth. This twisting motion takes the horizontal, east-west magnetic field lines and contorts them into new, small-scale, vertical loops that pop up through the sun's surface. These small loops then merge and coalesce, gradually regenerating the original, large-scale, north-south, or poloidal magnetic field, but with the opposite polarity. This is the dynamo in its full, beautiful complexity. Differential rotation takes a poloidal field and turns it into a strong toroidal field, and then convective. Twisted motions take that toroidal field and turn it back into a poloidal field. It is a self-sustaining, self-amplifying, and cyclical process, a magnetic engine that not only creates the sun's immense field, but also dictates its famous 11-year cycle of activity, a rhythm we will soon explore. This dynamo is not just a theoretical concept, we see its effects directly on the sun's surface. The twisted, buoyant tubes of magnetic field that are brought to the surface by convection emerge as the dark, complex regions we call sunspots, the very places where the sun's magnetic tension builds and from which solar flares and other eruptions are born. The sun's magnetic field, then, is not just a static presence, but a dynamic, ever-changing entity, constantly being generated, twisted, broken, and regenerated in the fiery depths of its plasma heart. It is this invisible, restless dynamo that ultimately writes the story of space weather, creating the conditions that can produce both the ethereal beauty of the aurora and the technological challenges of a geomagnetic storm, connecting the intricate physics of the solar interior to our daily lives in the most profound and unexpected ways. This magnificent solar dynamo, this engine of twisting plasma and regenerating magnetic fields, does not operate in a steady, constant state. Instead, it pulses with a slow, ancient, and remarkably predictable rhythm. It is a cosmic heartbeat that dictates the ebb and flow of solar activity, a grand cycle that takes, on average, about 11 years to complete. This is the solar cycle, and for astronomers, it is the fundamental metronome of our solar system, a conductor's baton that directs a symphony of phenomena from the sun's fiery surface to the very edge of our planet's atmosphere. To witness the solar cycle is to watch the sun's very personality transform, shifting from a state of serene, magnetic calm to a period of turbulent, energetic fury, and back again, in a pattern that has repeated itself with unwavering regularity for as long as we have had the tools to observe it. This rhythm is not merely an academic curiosity, it is the single most important factor in determining the space weather that our world experiences. And its gentle, predictable cadence is a profound testament to the underlying order that governs even the most seemingly chaotic of cosmic processes. The cycle begins in a period of quietude, a phase known as solar minimum. During these years, the sun's magnetic field is at its most simple and organized. It resembles the neat, orderly field of a bar magnet, with a clearly defined north magnetic pole and a south magnetic pole, and the field lines running in gentle, sweeping arcs between them. The sun's visible surface reflects this inner calm. It becomes a placid, almost unblemished golden sphere. Sunspots, those visible markers of magnetic turmoil, become rare, sometimes disappearing entirely for weeks or even months at a time. The sun's face is smooth, its expression tranquil. Solar flares and coronal mass ejections, the energetic outbursts of a restless star, become infrequent and relatively weak. For Earth, and for our technological civilization, this is a time of cosmic peace. The aurora retreat to their polar homes, shimmering only in the highest latitudes. The stream of solar particles, the solar wind, becomes a gentler, more predictable breeze. And the invisible shield of Earth's own magnetic field, the magnetosphere, settles into a state of quiet stability. The sun, it seems, is sleeping, and in its slumber, our corner of the solar system finds a period of welcome respite. But this peace is only a prelude. As the years pass, the dynamo deep within the sun's interior continues its relentless work. The differential rotation continues to stretch and twist the magnetic field lines, winding them tighter and tighter, injecting more and more energy into the system. The sun begins to awaken. The first signs of this re-emergence are the appearance of new sunspots, not at the equator, but at the middle latitudes, around 30 to 40 degrees north and south. These are the heralds of the new cycle, the first visible manifestations of the increasingly tangled magnetic field beginning to poke through the surface. As the cycle progresses, the number of sunspots steadily climbs, and they begin to migrate slowly towards the solar equator in a pattern so regular it is captured in what astronomers call the butterfly diagram. The sun's surface becomes increasingly mottled and complex, a canvas of magnetic activity. We are now entering the heart of the cycle, the turbulent and spectacular phase known as solar maximum. This is when our star's true power and complexity are on full display. The sun's magnetic field, now a tangled, chaotic mess of twisted loops and stressed arches, can no longer contain its stored energy. It releases it in brilliant, dramatic flashes. Solar flares become a near-daily occurrence, and powerful coronal mass ejections frequently hurl billions of tons of solar plasma out into the solar system. The sun is no longer sleeping. It is a restless, roaring giant. And then, at the very peak of solar maximum, the most remarkable event of the entire cycle occurs. The sun's global magnetic field completely reverses. The north magnetic pole, which may have been in the northern hemisphere of the sun, vanishes, and a new north magnetic pole emerges in the southern hemisphere. The south becomes north, and the north becomes south. This grand magnetic reversal is the culmination of the entire cycle, the moment when the dynamo completes its work of taking the old field, twisting it into chaos, and then regenerating a new field with the opposite orientation. After this magnetic flip, the sun's activity begins to wane. The tangled magnetic fields slowly simplify, sunspot numbers decline, and the sun begins its gentle slide back towards the calm and quiet of the next solar minimum. The entire 11-year cycle is, in essence, one half of a larger, 22-year magnetic cycle, which is the time it takes for the sun's magnetic field to go from north up to north down, and then back to north up again, returning to its original configuration. This cosmic heartbeat, this 11-year rhythm of quiet and storm, of order and chaos, and of magnetic birth, death, and rebirth, is the fundamental pulse of our solar system, a cycle that has been beating for billions of years, and a gentle reminder that even the stars themselves have seasons. As we continue to explore this cosmic heartbeat, this 11-year rhythm of our sun, we find ourselves drawn to the most visible and historically significant signs of its changing moods: the sunspots. These dark, ephemeral blemishes that drift across the solar surface are far more than mere curiosities for astronomers to catalogue. They are the windows into the sun's magnetic soul, the places where the star's immense and usually hidden interior turmoil breaks through to the surface and becomes visible to us, 93 million miles away. For centuries, since the first astronomers turned their newly invented telescopes toward the sun, we have been watching these spots, sketching their intricate forms, and tracking their patient, stately procession across the solar disk. In their dark, cool depths, we can read the story of the solar cycle, gauge the intensity of the sun's current activity, and even find the clues that help us predict the next powerful solar storm. They are the most direct and intimate connection we have to the workings of the magnetic dynamo, the physical evidence of the invisible forces that shape our star's very character. A sunspot, when viewed with the proper, heavily filtered telescope, is a breathtaking and complex structure. It is not merely a dark dot, but a region with a distinct and intricate anatomy. At its center lies the umbra, the darkest and coolest part of the spot, a place where the magnetic field is at its strongest and is oriented almost perfectly vertically, plunging straight down into the solar interior like the root of a colossal, invisible tree. Surrounding the umbra is the penumbra, a lighter, a filamentary region that resembles the petals of a celestial flower or the intricate pattern of an iris. Here, the magnetic field is weaker and more horizontal, with lines of force spreading out from the central umbra like the canopy of that magnetic tree. These sunspots are not cold in any absolute sense. The umbra of a large sunspot still seethes at a temperature of around 4,000 degrees Celsius, hotter than a blacksmith's forge. But they appear dark only in stark contrast to the even more brilliant 500-degree plasma of the surrounding photosphere. This cooling is a direct consequence of the intense magnetic field within the spot. The field lines are so strong and so densely packed that they act like a magnetic straitjacket, suppressing the normal convective motion of the hot plasma from below. The constant churning that normally brings fresh heat to the surface is effectively blocked, creating a cooler, and therefore darker, insulated region on the sun's face. Sunspots are not solitary phenomena. They are fundamentally social creatures. They almost always appear in pairs or in complex, sprawling groups, with the spots in a pair having opposite magnetic polarity, like the north and south poles of a horseshoe magnet. These pairs are connected by immense, invisible arches of magnetic field lines that loop high up into the sun's outer atmosphere, the corona. These coronal loops, sometimes stretching for hundreds of thousands of kilometers, are the true architecture of solar activity. They are the conduits that channel the flow of superheated plasma, the scaffolding upon which solar prominences condense, and most importantly, the places where magnetic energy is stored, twisted, and ultimately released in the violent events we call solar flares. When you see a group of sunspots, you are not just seeing dark patches, you are seeing the footprints, the anchor points, of a vast and complex magnetic structure that towers invisibly above the solar surface. The more complex the sunspot group, the more tangled and stressed these overlying magnetic loops are likely to be, and the greater the probability that they will snap and reconnect, unleashing a powerful burst of energy. Solar forecasters spend their days carefully studying the evolution of these sunspot groups, looking for signs of magnetic complexity spots with mixed polarities, or regions where magnetic fields are shearing past one another, as these are the telltale signs of an impending eruption. The life cycle of a sunspot group is a drama that plays out over days and weeks. A new group is often born as a simple pair of pores, which then grow and evolve into a large, complex active region, a sprawling archipelago of dozens of spots. After a period of peak activity, the group will begin to decay, its magnetic field weakening and dispersing until all that is left is the undisturbed, granulated pattern of the quiet sun. And as mentioned, their journey across the sun follows a predictable pattern, the butterfly diagram, appearing at mid-latitudes at the start of a cycle and migrating toward the equator as the cycle progresses. This migration is a direct visual tracer of the evolution of the sun's deep magnetic dynamo, a surface-level clue to the immense and slow transformations happening tens of thousands of kilometers below. For over 400 years, we have been counting them, tracking this rhythm, and in doing so, we have built a continuous record of the sun's heartbeat, a dataset that is one of the longest and most precious in all of science. These dark, fleeting spots are the language of the sun, and in learning to read them, we learn to understand the moods, the cycles, and the immense, magnetic power of our nearest, and most life-giving, star. It is from these regions of intense magnetic complexity, these sprawling, intricate archipelagos of sunspots, that the sun's most dramatic and powerful phenomena are born. High above the visible surface, in the ethereal, superheated tendrils of the solar corona, the immense magnetic loops that connect the sunspot pairs become twisted, sheared, and strained by the constant churning of the plasma below. They store enormous amounts of energy, like colossal, invisible rubber bands being wound tighter and tighter by an unseen hand. For hours, or even for days, this magnetic tension can build in a state of precarious equilibrium. But eventually, inevitably, a breaking point is reached. The field lines become so contorted that they can no longer maintain their structure, something has to give. And in a fraction of a second, in an event of almost instantaneous violence, they snap and reconfigure themselves into a simpler, more stable, lower energy state. This is the fundamental mechanism behind a solar flare, a process known to plasma physicists as magnetic reconnection. It is the moment the cosmic rubber band snaps, and the consequences of that snap are felt across the entire solar system. The release of energy during a magnetic reconnection event is almost incomprehensibly vast and efficient. In a matter of minutes, the stored magnetic energy is converted into a blinding flash of light and a furious acceleration of particles with an efficiency that no human-made engine could ever hope to match. The event begins with a sudden, brilliant brightening in the corona, a flash that can briefly outshine the entire rest of the sun's surface. This is the solar flare, and the energy it unleashes travels outward across the entire electromagnetic spectrum, from long-wavelength radio waves to the most energetic and deadly gamma rays. This burst of radiation, this first herald of the flare, travels at the speed of light, crossing the 93 million miles to Earth in just over 8 minutes. When it arrives, it washes over our planet's upper atmosphere. Its high-energy X-rays and extreme ultraviolet radiation slamming into the atoms and molecules of the ionosphere, stripping them of their electrons and causing a sudden, dramatic increase in ionization. This can trigger an immediate radio blackout on the sunlit side of the Earth, particularly for high-frequency communications used by aviation and emergency services. For a few minutes to a few hours, the sky is no longer a transparent window for these signals, but an absorbent, turbulent barrier. But the flare is not just a flash of light. The same magnetic reconnection event that produces the radiation also acts as a colossal particle accelerator, one of the most powerful in the entire solar system. It takes the ambient plasma of the corona, the protons and electrons, and accelerates them to incredible speeds, some approaching a significant fraction of the speed of light. This spray of high-energy particles streams out from the sun, following the newly reconfigured magnetic field lines like cars on a cosmic highway. These solar energetic particles, or SEPs, travel more slowly than the light of the flare, but still reach Earth within a matter of minutes to hours. When they arrive, they pose a significant radiation hazard to anything outside the protective blanket of our atmosphere. Astronauts aboard the International Space Station must take shelter in the most shielded parts of their craft. Satellites can have their sensitive electronics damaged or scrambled by these high-velocity impacts. And even passengers and crew on commercial airliners flying high-altitude polar routes can receive a measurable increase in their radiation dose, which is why such flights are sometimes rerouted during a major solar particle event. Solar flares are classified by their intensity, measured by the peak X-ray brightness, using a system that might remind you of how earthquakes are measured. The smallest flares are called A-class, followed by B, C, M, and the most powerful, X-class flares. Each letter represents a 10-fold increase in energy output. So an X-class flare is 10 times more powerful than an M-class, and 100 times more powerful than a class. The most powerful flare ever definitively recorded, in 2003, was so intense it saturated the detectors on our solar observatories. It was rated as an X-28, an event of truly awesome and terrifying power, a reminder that our seemingly stable star is capable of unleashing energies that test the very limits of our scientific scales. The snap of that magnetic rubber band is not just a distant, academic event. It is a profound and direct connection between the plasma physics of a star's atmosphere and the delicate technological infrastructure upon which our modern civilization has come to depend. But solar flares, as spectacular and energetic as they are often only the first act in a much larger and more consequential solar drama. The sudden, brilliant flash of radiation is sometimes just the precursor, the muzzle flash from a cannon that has just fired something far more substantial across the solar system. Often, and especially in the case of the largest and most powerful flares, the same magnetic reconnection event that triggers the flare also destabilizes the entire magnetic structure above it, leading to the eruption of a coronal mass ejection, or CME. This is not just a burst of energy. This is the sun physically hurling a piece of itself out into space. Imagine a colossal magnetic bubble, a twisted, rope-like structure of magnetic field lines and trapped plasma that has been held down for days by the overlying magnetic field of the corona. When the reconnection event occurs below it, it can act like a trigger, cutting the magnetic tethers that have been holding this bubble in place. Released from its confinement, the bubble expands and accelerates outward with ferocious speed, launching billions of tons of the sun's own atmosphere, a magnetized cloud of plasma, into interplanetary space. This is a CME, and if a solar flare is like a lightning strike, a CME is like a hurricane, a slower, more massive, and often far more impactful event for our planet. Unlike the radiation from a flare, which travels at the speed of light and arrives at Earth in a mere 8 minutes, a CME is a ponderous, lumbering giant. It is a cloud of actual matter, and so it must traverse the 93 million miles of space physically. The fastest CMEs can make the journey in as little as 15 to 18 hours, traveling at speeds of thousands of kilometers per second. More typical CMEs are a bit more leisurely, taking anywhere from 1 to 4 days to arrive. This transit time is a profound gift. It gives us a crucial window of warning. Our fleet of solar observatories, like the Solar and Heliospheric Observatory, SOHO, are positioned in a way that allows them to see the sun from the side. They can directly image a CME as it leaves the sun, a great, expanding halo of light billowing out into space. By tracking its speed and direction, scientists can predict, with a reasonable degree of accuracy, if it is heading toward Earth and when it is likely to arrive. This allows space weather forecasters to issue alerts to satellite operators, power grid managers, and airlines, giving them precious hours or days to brace for the storm's impact. The structure of a CME is far more complex than a simple cloud of gas. It is a coherent, organized magnetic entity, a piece of the sun's own magnetic field that has been disconnected and is now traveling through space. It often has a distinct, rope-like magnetic structure, known as a flux rope, and it carries within it the dense, hot plasma of the solar corona. As this magnetized cloud expands and travels through the solar system, it plows through the slower, ambient solar wind, creating a shockwave ahead of it, much like the bow wave of a speeding boat. It is this complex, internal magnetic field of the CME that is the key to its interaction with Earth. When this massive magnetic bullet finally arrives at our planet, it does not simply collide with our atmosphere. Instead, it first encounters Earth's own magnetic field, our magnetosphere, and the real show begins. The interaction between the CME's magnetic field and our planet's magnetic field can be gentle, or it can be catastrophically violent, depending entirely on the orientation of the magnetic fields involved. This is the moment when the slow, patient journey of a piece of the sun finally culminates in a direct and powerful conversation with our own world, a conversation written in the language of plasma and magnetism, and one that can have the most beautiful and the most dangerous of consequences. With its birth in the fiery, reconfiguring corona, the coronal mass ejection embarks on its grand interplanetary journey, a silent, majestic voyage across the vast and seemingly empty expanse that separates our world from its star. This is not a journey through a true vacuum. The space between the planets is filled with a tenuous, but ever-present medium, the solar wind. This is a constant, a steady stream of charged particles, mostly protons and electrons, that are continuously evaporating from the sun's hot corona and flowing outward in all directions at speeds of hundreds of kilometers per second. It is the sun's perpetual exhalation, a cosmic breeze that shapes the magnetic environments of all the planets, pushes the tails of comets away from the sun, and defines the very boundaries of our solar system. A CME, upon its eruption, is like a supersonic jet punching its way through this much slower, more gentle wind. It is a discrete, coherent stormfront moving through a pre-existing weather pattern, and its journey is one of expansion, interaction, and propagation, a story that unfolds over millions upon millions of kilometers. As the CME travels, it expands dramatically. The magnetic pressure inside the cloud, no longer constrained by the immense gravity and magnetic fields of the sun, causes it to swell to an enormous size. By the time it reaches Earth's orbit, a single CME can be tens of millions of kilometers across, a cloud so vast it could swallow our planet dozens of times over. This expansion means that even if a CME is not aimed directly at Earth, we can still be grazed by its flank, feeling the effects of a storm whose core has passed us by. The journey is also a dynamic one. The CME's path is not a perfectly straight line, but is guided and deflected by the large-scale magnetic field of the heliosphere, the Parker spiral. This gentle, curving structure of the interplanetary magnetic field, which is dragged out from the sun by its rotation, can sometimes steer a CME slightly north or south of the ecliptic plane, causing a storm that looked initially Earth-directed to miss us entirely, or vice versa. Predicting this subtle deflection is one of the greatest challenges for space weather forecasters. A cosmic game of billiards played across a table 93 million miles long. The most crucial part of this interplanetary journey, however, is what happens within the CME itself. As it travels, its internal magnetic field evolves. The orientation of the magnetic field lines within the CME's flux rope can rotate and change, and it is this orientation at the moment of impact with Earth that will determine the severity of the resulting geomagnetic storm. Specifically, what matters most is the southward component of the magnetic field. Earth's own magnetosphere has a northward-pointing magnetic field at its sunward boundary. If the arriving CME also has a northward-pointing field, the two magnetic systems will drape over each other, like two magnets, with their like poles pushed together. The interaction will be relatively mild, and much of the CME's energy will be deflected around our planet. But if the CME's magnetic field is pointing southward, opposite to Earth's, then the stage is set for a dramatic and efficient energy transfer. The oppositely directed field lines can undergo magnetic reconnection at the boundary of our magnetosphere, effectively opening a door, a magnetic portal, that allows the vast energy and plasma of the CME to pour directly into our planet's protective magnetic shield. This is the secret handshake, the specific magnetic key that unlocks the gates of our world to the full fury of a solar storm. After a silent journey of 1 to 4 days, after traveling across a gulf of space that has separated it from its stellar parent, the CME finally arrives at our doorstep. The shockwave at its leading edge is the first to make contact, announcing the storm's arrival with a sudden jolt to our magnetosphere, a compression that can be detected by magnetometers on the ground. And then, for the next several hours, our planet will be enveloped, bathed in a piece of the sun itself, beginning a direct, and often spectacular, conversation with the star that gives it life. As the colossal, the magnetized cloud of the coronal mass ejection finally reaches the end of its interplanetary journey, it does not encounter a naked, defenseless planet. It meets a guardian, an invisible, formidable, and life-sustaining shield that has been protecting our world for billions of years. This is Earth's magnetosphere, a vast, dynamic, and complex magnetic bubble that extends tens of thousands of kilometers out into space, a silent sentinel standing guard against the constant onslaught of the solar wind and the occasional fury of a solar storm. It is our planet's own force field, a gift from the deep interior, and without it, the history of life on Earth, and indeed the very presence of our atmosphere and oceans, would have been profoundly and perhaps impossibly different. To understand the cosmic drama that is about to unfold, we must first appreciate the nature and origin of this remarkable planetary shield. The magnetosphere is not a static, solid shell. It is a dynamic entity, generated deep within our planet's core. The Earth's core is composed of a solid inner sphere of iron, surrounded by a vast, churning ocean of molten iron and nickel. The immense heat flowing out from the inner core creates powerful convective currents in this liquid outer core, much like the boiling plasma within the Sun. And, just as in the Sun, the combination of this motion of an electrically conductive fluid and the planet's rotation creates a self-sustaining dynamo. This terrestrial dynamo generates Earth's global magnetic field, a field that is, at its most basic level, similar to that of a simple bar magnet, with a north and a south pole. This magnetic field does not stop at the planet's surface. Its lines of force extend far out into space, creating the vast, protective structure of the magnetosphere. It is a direct, physical connection between the churning, molten heart of our world and the vacuum of space, a planetary-scale projection of our world's inner life. In its normal quiet state, the magnetosphere has a distinct and beautiful shape, sculpted not by the Earth itself, but by the relentless pressure of the ever-present solar wind. On the side of the Earth facing the Sun, the day side, the magnetosphere, is compressed by the solar wind into a rounded, bullet-like shape, with its boundary, the magnetopause, located at a distance of about 10 Earth radii, or roughly 64,000 kilometers. On the side of the Earth, facing away from the Sun, the night side, the magnetosphere, is stretched out by the solar wind into a long, cylindrical tail, the magnetotail, that extends for millions of kilometers, far beyond the orbit of the Moon. This is our planet's magnetic signature in the solar system, a shape as unique and recognizable as the rings of Saturn. Within this magnetic bubble, life on Earth is almost completely shielded from the direct impact of the solar wind and the much more energetic and deadly cosmic rays that originate from deep space. The magnetosphere acts as a great deflector, forcing the majority of these charged particles to flow around our planet, like water around a boulder in a stream. It is this protection that has allowed Earth to retain its atmosphere over geological timescales, preventing the solar wind from slowly stripping it away, particle by particle, a fate that befell Mars after it lost its own global magnetic field billions of years ago. Now, picture this guardian field as the CME arrives. The initial shockwave of the storm front hits the magnetopause like a physical blow, a sudden increase in the solar wind's pressure that compresses the entire dayside magnetosphere, sometimes pushing its boundary inward to half its normal distance. On the ground, sensitive magnetometers register this sudden compression as a sharp jolt, and then the main body of the CME cloud, with its embedded magnetic field, washes over the planet. As we discussed, if the CME's magnetic field is pointing northward, aligned with Earth's, the shield holds strong, and the storm passes with relatively minor effects. But if the CME's field is pointing southward, the gates are thrown open. Magnetic reconnection begins on a massive scale at the magnetopause, merging the solar and terrestrial magnetic fields and creating a direct conduit for energy and plasma to pour into our system. The guardian field, for a time, becomes a welcoming host, inviting the storm inside, an act that is both the source of the aurora's breathtaking beauty and the root cause of all the technological havoc a geomagnetic storm can wreak. Once that magnetic gateway is opened, once the southward-pointing field of the coronal mass ejection reconnects with the northward-pointing field of our planet's dayside magnetosphere, the true celestial spectacle begins. The immense energy and the billions of tons of solar plasma that have traveled for days across the void now have a direct pathway into our world's magnetic domain. But this is not a chaotic, uncontrolled flood. Instead, The energy is captured and channeled by the newly reconfigured magnetic field lines in a process of incredible scale and elegance. The solar magnetic field lines, now stitched together with Earth's, are draped over the planet and dragged by the solar wind into the long, dark magnetotail that stretches out behind us. The magnetotail becomes a colossal reservoir of stored energy. Its two lobes, one with a northward-pointing field and one with a southward-pointing field, becoming increasingly stretched and loaded with the captured solar plasma, like a cosmic slingshot being pulled further and further back. For a time, this stretched configuration can hold, but the tension builds until it, too, reaches a breaking point. Deep within the magnetotail, hundreds of thousands of kilometers behind the Earth, another massive magnetic reconnection event occurs. The stretched field lines suddenly snap back toward the planet with tremendous force. This snapping of the magnetotail slingshot is the engine that powers the aurora. It accelerates the trapped electrons and protons back towards the Earth along the magnetic field lines with incredible speed and energy. These accelerated particles, now a focused and energetic beam, behave like charged particles in an old cathode ray television set, guided precisely by the magnetic field. And Earth's magnetic field funnels them, with perfect efficiency, towards the planet's magnetic poles. As this rain of high-energy solar and magnetotail particles, this invisible beam fired from a slingshot 1,000,000 kilometers away, plunges down into the upper reaches of our atmosphere. The final, beautiful act of this cosmic play unfolds. At altitudes of 100 to 400 kilometers, these energetic particles begin to collide with the atoms and molecules of the thin, cold air, primarily oxygen and nitrogen. Each collision is a tiny, microscopic transfer of energy. The incoming particle excites the atmospheric atom, kicking one of its electrons into a higher, more energetic orbit. But this excited state is unstable and cannot last. Within a fraction of a second, the electron falls back to its original energy level, and in doing so, it releases the extra energy it had absorbed in the form of a single, pure particle of light, a photon. This process, repeated trillions upon trillions of times, is what creates the aurora. The sky does not glow, it is actively being painted with light, molecule by molecule, by a stream of particles from the sun, guided by the Earth's magnetic field. The specific colors of this celestial light show are a direct consequence of the type of atom being struck and the altitude at which the collision occurs, a form of celestial neon sign. The most common color, a brilliant, vibrant, green, is produced by collisions with oxygen atoms at altitudes of around 100 to 240 kilometers. Higher up, where the atmosphere is even thinner, collisions with oxygen can produce the rarer, beautiful, deep red hues that often shimmer at the very top of an auroral display. Collisions with nitrogen molecules, the most common gas in our atmosphere, are responsible for the blues and purples that can sometimes be seen at the lower edges of the auroral curtain. During a powerful geomagnetic storm, this process is supercharged. The auroral ovals, the rings of light that are normally confined to the high polar regions, expand dramatically, pushing down into the mid-latitudes. The aurora is no longer a distant, faint shimmer on the northern horizon, but a sky-filling, dynamic, and breathtaking display. It takes on complex and rapidly changing forms, great, shimmering curtains that ripple and wave as if blown by an unseen wind, pulsating patches that flash on and off, and great, towering rays that seem to converge at a single point overhead, creating a magnificent auroral corona. This is not just a light show, it is a direct, visual manifestation of the invisible magnetic storm raging in the space around our planet. A beautiful and powerful reminder of our world's profound and ongoing connection to its parent star. While the aurora paints the polar skies with a light show of ethereal and breathtaking beauty, the very same geomagnetic storm that creates it can cast a dark and disruptive shadow over the intricate technological civilization we have built on the ground. The dazzling display in the upper atmosphere is merely the visible symptom of a planet-wide magnetic disturbance, a storm that can stress, disrupt, and sometimes even destroy the very systems that underpin modern life. The same invisible forces that guide solar particles to create curtains of light can also induce unwanted, damaging currents in the vast networks of metal that span our continents. This technological vulnerability is a relatively new aspect of our ancient relationship with the sun, a consequence of a world that has, in just over a century, wrapped itself in a delicate, conductive web of power lines, communication cables, and satellite networks. For us, the sun's fury is no longer just a matter of celestial wonder. It is a matter of profound practical and economic concern. The most significant and direct threat is to our electrical power grids. During a major geomagnetic storm, the rapid fluctuations in Earth's magnetic field induce powerful electrical currents in the ground, a phenomenon known as geomagnetically induced currents, or GICs. These currents naturally seek the path of least resistance, and there are no better paths than the hundreds of thousands of kilometers of high-voltage transmission lines that act like giant antennas, soaking up this unwanted energy. These are not the alternating currents, AC, that power grids are designed to handle, but slow-varying, quasi-direct currents, DC. When these GICs flow into the massive transformers at electrical substations, they can cause a condition called half-cycle saturation. The transformer's iron core becomes magnetically saturated, causing it to overheat dramatically, operate inefficiently, and generate a cascade of harmonic distortions that can destabilize the entire grid. In a worst-case scenario, the transformer's windings can literally melt, causing catastrophic failure and a long-term blackout, as these massive, custom-built devices can take months or even years to replace. This is precisely what happened in March 1989, when a powerful geomagnetic storm caused the entire power grid of Quebec, Canada, to collapse in less than 90 seconds, leaving 6 million people in the dark for 9 hours, and demonstrating with chilling clarity just how vulnerable our modern infrastructure can be. Our satellites, those silent, indispensable sentinels orbiting high above the atmosphere, are on the front lines of any solar storm. They are directly exposed to the full, unfiltered fury of the event. The high-energy particles that arrive with a solar flare can cause single-event upsets, where a particle strikes a microchip and flips a bit from a 0 to a 1, leading to phantom commands or software glitches. More seriously, a sustained bombardment of particles can lead to a buildup of electrical charge on the satellite's surface, a phenomenon called surface charging. This can lead to a powerful electrostatic discharge, a miniature lightning strike, that can permanently fry sensitive electronics. During a geomagnetic storm, the entire radiation environment of near-Earth space changes dramatically. The Van Allen belts can become supercharged with killer electrons, and the upper atmosphere itself heats up and expands. This atmospheric drag is a particular problem for satellites in low Earth orbit, like the International Space Station and the thousands of satellites that make up constellations like Starlink. The increased drag can cause their orbits to decay more rapidly, requiring them to use precious fuel to boost themselves back up, and making their positions harder to predict, increasing the risk of collision. And finally, our modern world's profound reliance on the Global Positioning System, GPS, creates another critical vulnerability. GPS works by receiving incredibly precise timing signals from a constellation of satellites. During a solar storm, the same ionization in the ionosphere that causes radio blackouts can also delay and scintillate these GPS signals as they pass through, introducing errors in their timing that can throw off positioning by tens of meters. For industries like aviation, precision agriculture, and high-frequency financial trading, where timing is everything, such an outage can have immediate and costly consequences. The sun's shadow, then, is a long one, capable of reaching from the distant corona to the delicate circuits of a smartphone, a quiet but powerful reminder that in our quest to build a globally connected, technological world, we have also, unintentionally, made ourselves citizens of a much larger and much wilder solar system. To truly understand the profound vulnerability of our modern, electrified world to a major solar storm, we must drift back in time to an era before the global power grid, before satellites, before the very concept of space weather even existed. We must journey back to the late summer of 1859, a time of steamships and telegraphs, to witness a solar storm of such legendary and terrifying power that it remains the benchmark, the great perfect storm against which all other solar events are measured. This was the Carrington event, a geomagnetic storm so intense that it set the scientific world alight with wonder and fear, and provided a chilling preview of what a truly extreme solar tantrum could do to a technological civilization, even one as nascent as that of the mid-19th century. Its story serves as a stark and humbling warning, a historical ghost that haunts the nightmares of modern emergency planners. The story begins on the morning of September 1st, 1859, with a dedicated amateur astronomer named Richard Carrington. From his private observatory in Redhill, England, he was engaged in his daily, patient task of sketching the sunspots that dotted the sun's face. Suddenly, he witnessed something no one had ever knowingly seen before. Within a large and complex sunspot group, two brilliant, blindingly white points of light appeared, two patches of intensely bright and white light, as he later wrote. They were so intense they outshone the sun's surface itself. Carrington, initially thinking a stray beam of light had contaminated his telescope, quickly realized he was witnessing a cataclysmic event on the sun itself. He had, by sheer luck and diligence, become the first person to observe a white light solar flare. The event lasted only 5 minutes, but what it unleashed was already on its way to Earth. Unbeknownst to Carrington, this colossal flare had launched a coronal mass ejection of almost unbelievable speed and ferocity directly at our planet. While a typical CME takes several days to make the journey, this one, supercharged by an earlier CME that had cleared the path for it, made the 93 million-mile trip in a record-breaking 17.6 hours. When this magnetic cannonball struck Earth's magnetosphere in the early hours of September 2nd, the planetary guardian field was overwhelmed. The resulting geomagnetic storm was, by every available measure, the most intense in recorded history. The most beautiful and immediate effect was a display of the aurora of a scale and brilliance that has not been seen since. The northern lights, normally a ghostly shimmer confined to the Arctic, exploded into a global phenomenon. They were seen as far south as Cuba, the Caribbean, and even Colombia, near the equator. The light was so intensely bright that newspapers from the era are filled with accounts of people being woken up in the middle of the night, thinking it was dawn. Gold miners in the Rocky Mountains got up and started making breakfast. In the northeastern United States, people could read a newspaper by the aurora's light alone. The sky was filled not with gentle, shimmering curtains, but with roiling, blood-red and crimson sheets of light that pulsated and shifted with terrifying speed. It was a spectacle of profound, and for many, deeply unsettling, beauty, but it was in the nascent technological network of the 19th century, the global telegraph system, that the Carrington event's true power was most dramatically felt. The same geomagnetically induced currents that we now worry about in our power grids surged through the thousands of miles of telegraph wires that crisscrossed Europe and North America. The currents were so strong that they completely overwhelmed the weak electrical signals of the telegraphs. Telegraph operators reported receiving powerful electric shocks from their equipment. Sparks literally flew from the telegraph keys. Pylons were seen to throw off sparks as the wires hummed with unseen energy. In some cases, The induced currents were so powerful that they caused the telegraph paper to spontaneously catch fire. The most astonishing reports, however, came from operators who, in a moment of scientific curiosity, disconnected their batteries, the wet cell power sources of the day, and found that they could continue to send and receive messages, sometimes with even greater clarity, powered by the aurora itself. The planet's own magnetic field had become a giant and dangerously unpredictable battery. For a few hours, human communication was being directly powered by a storm on the sun. Now, drift forward in time and imagine what a storm of that magnitude, a true Carrington-class event, would do to our modern world. The consequences are almost too daunting to contemplate. A 2013 study by Lloyd's of London estimated that the initial financial costs of such an event could range from $0.6 to $2.6 trillion in the United States alone. Widespread, long-lasting blackouts could affect hundreds of millions of people, as hundreds of the massive, hard-to-replace transformers that form the backbone of the grid could be destroyed simultaneously. The global satellite network, upon which our GPS, communications, and financial systems depend, would be severely degraded, with many satellites potentially lost for good. The intricate, just-in-time global supply chains would grind to a halt. We would be plunged, in an instant, into a world without the fundamental infrastructure that supports modern life. It would be a new kind of darkness, a technological silence imposed upon us by our own star. The Carrington event is not just a historical curiosity, it is a warning shot, a reminder that we live in the crosshairs of a star that is capable of a power we are still only beginning to understand, and that our own incredible technological progress has also, in a quiet and profound way, made us more fragile than ever before. In the face of such a profound and potentially devastating threat, humanity has not been idle. We have not simply resigned ourselves to the whims of our star, but have, in a quiet and steady revolution, turned our own technological ingenuity toward the heavens, creating a new and vital field of science dedicated to understanding and predicting the sun's moods. This is the science of space weather forecasting. It is a field born from the recognition of our own vulnerability, a global, collaborative effort to keep a constant, unblinking watch on the sun, to listen for its magnetic whispers, and to provide the precious, critical moments of early warning that could make the difference between a manageable disruption and a global catastrophe. We have, in essence, become celestial meteorologists, charting the storms not of our own atmosphere, but of the star that makes our atmosphere possible. And our weather stations are not on the ground, but are sophisticated, robotic sentinels, positioned strategically in the vast emptiness of space. The cornerstone of this global effort is a fleet of dedicated, space-based solar observatories, telescopes of incredible power and sophistication that have revolutionized our understanding of the sun. One of the most venerable and important of these is the Solar and Heliospheric Observatory, or SOHO, a joint mission between NASA and the European Space Agency that has been watching the sun continuously for nearly 3 decades. SOHO is not in orbit around the Earth. Instead, it is strategically positioned at a unique point in space called the Lagrange Point 1, or L1, located about 1.5 million kilometers from Earth in the direction of the sun. From this privileged vantage point, SOHO has a constant, uninterrupted view of our star, a front-row seat to the entire solar drama. Its most critical instrument for space weather forecasting is its coronagraph, a device that uses a small, occulting disk to block out the blindingly bright face of the sun itself, creating an artificial eclipse. This allows it to see the much fainter, ethereal corona, and most importantly, to directly image a coronal mass ejection as it erupts and billows out into space. When SOHO sees a large, fast halo CME negative, one that appears to expand in a circle around the sun, forecasters know it is likely heading directly for Earth. Joining SOHO is the more modern and even more powerful Solar Dynamics Observatory, or SDO. In a geosynchronous orbit around the Earth, SDO is a data-generating behemoth, capturing an image of the Sun every 0.75 seconds in 10 different wavelengths of extreme ultraviolet and ultraviolet light. This allows scientists to see the Sun's magnetic field and its superheated corona in unprecedented detail, to watch the intricate dance of coronal loops as they twist and evolve, and to pinpoint the exact moment and location of a solar flare. SDO is our primary tool for monitoring the sunspot groups and active regions that are the source of space weather, allowing forecasters to assess their complexity and their potential for eruption. Together, SOHO's broad view and SDO's detailed, multi-wavelength imagery provide a comprehensive and near real-time picture of what the Sun is doing. This constant stream of data flows down to forecasting centers around the world, like the Space Weather Prediction Center, SWPC, in Boulder, Colorado, which is part of the U.S. National Oceanic and Atmospheric Administration, NOAA. Here, human forecasters and sophisticated computer models work around the clock, 24/7, to analyze the data, issue watches, warnings, and alerts, and communicate the threat to government agencies and critical infrastructure operators. When a major, Earth-directed CME is detected, the clock starts ticking. The forecasters will model its trajectory and speed to predict its arrival time, and they will issue a warning. A power grid operator might then take protective measures, such as reducing the load on the system or temporarily taking particularly vulnerable transformers offline to prevent them from being damaged. Satellite operators might put their spacecraft into a protective, safe mode, turning off non-essential, sensitive electronics to help them ride out the storm. Airlines will be alerted to the impending radiation storm, allowing them to reroute polar flights to lower, safer latitudes. And even the teams that manage the precise timing of the GPS network can prepare for the ionospheric disturbances that will inevitably come. The science of space weather forecasting is still young and far from perfect. Predicting exactly when a particular sunspot group will erupt remains a profound challenge, much like predicting the exact moment an earthquake will strike. But our ability to see a storm after it has left the Sun and to predict its arrival at Earth has transformed our relationship with our star from one of helpless victim to one of prepared and vigilant observer. These watchers of the Sun, these silent, robotic outposts and their dedicated human interpreters, are the unsung heroes of our modern technological age, the guardians who watch the fire so that we may continue to live safely in its gentle, life-giving warmth. As our understanding of the Sun's magnetic personality has deepened, we have begun to uncover a connection that is far more subtle, more complex, and perhaps even more profound than the immediate, dramatic impacts of a solar storm. We are beginning to discern the faint, but persistent, the signature of the Sun's 11-year cycle and its longer-term variations woven into the very fabric of Earth's climate. This is a field of science filled with intricate debate and tantalizing clues, a place where the grand, celestial rhythms of a star may have a quiet, but significant, influence on the long-term patterns of our planet's weather, the health of our oceans, and the very conditions that have allowed our civilization to flourish. This is not to say that the Sun is the primary driver of the rapid climate change we are experiencing today. That responsibility lies overwhelmingly with human activities. But the Sun is a powerful background character in our climate story, a variable that has been modulating Earth's thermostat on timescales of decades, centuries, and millennia, long before we ever began to play our own, more dominant, a role. The most direct and obvious way the Sun could influence our climate is through changes in its total energy output, what scientists call total solar irradiance, TSI. For a long time, the Sun was referred to as the solar constant, as it was believed its brightness never changed. But with the advent of precise satellite measurements, we have discovered that this is not true. The sun's brightness does vary, but only by a very small amount. Over the course of a typical 11-year solar cycle, the difference in the amount of energy reaching the Earth between the peak of solar maximum and the trough of solar minimum is only about 0.1%. This is a tiny fluctuation, and by itself, it is not enough to cause the significant climate shifts we see in the historical record. But this small change in total light may be the tip of a much larger and more complex iceberg, as the changes in specific wavelengths of light and in the sun's magnetic activity are far more dramatic. During solar maximum, for instance, the output of extreme ultraviolet EUV radiation can increase by a factor of 10 or more. This EUV radiation is absorbed high in our atmosphere, in the stratosphere, where it plays a crucial role in creating and destroying ozone. A more active sun heats the stratosphere more, which can subtly alter the patterns of major atmospheric circulation systems, like the jet stream, influencing storm tracks and regional weather patterns across the globe. Perhaps the most intriguing, and still debated, connection lies in the relationship between the sun's magnetic field, cosmic rays, and clouds. The heliosphere, that great magnetic bubble created by the solar wind, acts as a partial shield for our entire solar system, deflecting a significant portion of the high-energy galactic cosmic rays that are constantly streaming in from interstellar space. When the sun is magnetically active, at solar maximum, its magnetic field is stronger and more turbulent, providing a more effective shield. This means fewer cosmic rays reach Earth. When the sun is quiet, at solar minimum, the shield weakens, and more cosmic rays penetrate our atmosphere. The theory, proposed by scientists like Henrik Svensmark, is that these cosmic rays, when they strike our atmosphere, can act as seeds for cloud formation by creating ions that help water vapor condense into droplets. If this is true, then the solar cycle could directly modulate the amount of cloud cover on Earth. More cosmic rays at solar minimum could mean more clouds, and since low-level clouds have a net cooling effect by reflecting sunlight back to space, this could lead to slightly cooler global temperatures. Fewer cosmic rays at solar maximum could mean fewer clouds and slightly warmer temperatures. This cosmic ray lever could potentially amplify the small 0.1% change in direct solar heating into a more significant climate signal. The historical evidence for such a connection is compelling, if not yet conclusive. The most famous example is the Maunder minimum, a period from roughly 1645 to 1715, when sunspots, the visible markers of the solar cycle, virtually disappeared from the sun's face for 70 years. This prolonged solar minimum coincided almost perfectly with the coldest part of a multi-century cool period in the northern hemisphere, known as the Little Ice Age. Tree rings and ice cores from this period show elevated levels of isotopes like carbon-14 and beryllium-10, which are produced when cosmic rays strike the atmosphere, confirming that the sun's magnetic shield was indeed exceptionally weak during this time. While this correlation does not prove causation, volcanic activity also played a role in the Little Ice Age's cooling. It provides a powerful hint that a star that is magnetically sleeping for a long time can have a noticeable effect on the climate of the worlds that orbit it. The sun's influence, then, is not just a story of sudden storms, but of slow, subtle, and persistent rhythms, a quiet magnetic hand on the tiller of our planet's long-term climate, a connection that we are only just now, with our most sophisticated tools and our deepest historical records, beginning to fully and humbly appreciate. As our scientific gaze penetrates deeper into the intricate web of connections between our star and our world, we are beginning to uncover a frontier of inquiry that is, in many ways, the most intimate and mysterious of all. We are finding the faint, but persistent, whispers of the sun's magnetic influence, not just in our technologies or our climate, but within the very fabric of life itself. For billions of years, life on Earth has evolved and flourished under the constant, rhythmic pulse of the sun's magnetic heartbeat and the steady shield of our own planet's magnetic field. It is perhaps no surprise, then, that some organisms may have evolved to sense and respond to this invisible, fundamental force of their environment. This is the science of magnetoreception, the study of the biological compass, a field that explores the tantalizing and often elusive evidence that living creatures, from the smallest bacteria to the largest whales, can perceive and utilize magnetic fields to navigate their world, and how a storm on the sun might, in a very real sense, cause them to lose their way. The most compelling evidence for this remarkable sense comes from the world of migratory animals. Every year, countless birds, sea turtles, fish, and even insects embark on epic journeys of thousands of kilometers, navigating with a precision that has baffled scientists for centuries. A tiny Arctic tern, for example, can travel from the North Pole to the South Pole and back again, returning to the very same nesting ground from which it departed. How does it achieve such a feat? While they are known to use multiple cues, including the position of the sun and the stars, a growing body of evidence suggests that many of these animals possess an internal, biological magnetic compass. They can literally feel the lines of force of the Earth's magnetic field, using its inclination angle and intensity as a kind of natural, global GPS to determine their latitude and their direction. The exact mechanism behind this sense is still a subject of intense scientific debate, but one leading theory, the radical pair mechanism, suggests that it may all happen at the quantum level. In this model, a special type of molecule in the animal's eye, a cryptochrome, when struck by a photon of light, can create a pair of electrons that are quantumly entangled. The orientation of these entangled electrons is exquisitely sensitive to the direction of an external magnetic field, which in turn could affect the molecule's chemistry, sending a signal to the animal's brain that is effectively a visual pattern of the magnetic field, superimposed upon its normal vision. They might, in a very real sense, be able to see the magnetic field of the Earth, and this is where the sun's moods enter the biological story. During a major geomagnetic storm, the Earth's magnetic field, the very map these creatures rely on, becomes distorted, disturbed, and wildly unpredictable. The normally reliable lines of force can bend and shift, and the intensity can fluctuate dramatically. For a migratory animal, this would be akin to a human hiker trying to navigate through a blizzard with a compass needle that is spinning wildly and uncontrollably. There are numerous, well-documented cases that correlate with this idea. Homing pigeons, famous for their incredible navigational ability, have been shown to become disoriented and lose their way when released during a geomagnetic storm. There are also unsettling, though not yet definitively proven, correlations between major solar storms and mass strandings of whales and dolphins, creatures that are also believed to use the magnetic field to navigate the vast, featureless expanses of the open ocean. It is a poignant and unsettling thought that a violent magnetic reconnection event in the sun's corona could, a few days later, cause a pod of majestic whales to fatally lose their bearings and wash ashore on a distant beach. The potential influence of solar storms may even extend to our own human biology, though this is a far more speculative and controversial area of research. The human body is, after all, an electrochemical system. Our nerve impulses are electrical signals, and our heart rhythms are governed by precisely timed electrical pacemakers. For decades, researchers, particularly in Eastern Europe, have compiled statistical studies suggesting correlations between periods of high geomagnetic activity and an increase in the incidence of heart attacks, strokes, and even psychiatric admissions. The proposed mechanisms are still poorly understood, and the correlations are often weak and debated. But it is not entirely outside the realm of possibility that the same magnetic storms that can induce destructive currents in a power grid could have some subtle, but measurable, effect on the delicate bioelectrical processes within our own bodies. This is a frontier of science where we must tread with caution and skepticism, but also with an open and curious mind. For life has proven, time and again, to be more sensitive and more deeply connected to its environment than we have often given it credit for. The sun's magnetic influence, then, may not stop at the boundaries of our atmosphere, or even at the circuits of our machines, but may, in some quiet, a subtle way that we are only just beginning to learn how to listen for, reach all the way down into the very beat of our own hearts. As our gentle journey through the cosmos draws toward its final, quiet close, we find ourselves drifting back from the distant stars and the fiery heart of the sun, returning to this present moment, to the simple, profound reality of our own existence. We have traced the grand, sweeping arc of gravity's influence, from the first faint whispers of structure in the infant universe to the intricate, stable dance of our own solar system. We have followed the more volatile and electric story of magnetism, from its birth in the churning dynamo of the sun to its beautiful and sometimes disruptive encounters with our own world. Now, in these final, peaceful moments, we are invited to weave these two great stories together, and to recognize that they are not separate narratives, but two harmonious parts of a single, magnificent composition. And the subject of that composition, the place where all these cosmic forces converge, is you. You are not a passive observer of this cosmic ballet. You are an integral and inseparable part of it, a living, breathing testament to the profound interconnectedness of all things. Consider, for a moment, the atoms that make up your body, the carbon that forms the backbone of your DNA, the oxygen you are breathing in this very moment, the calcium in your bones, and the iron in your blood. None of these were created on Earth. They are stardust, forged in the incomprehensible heat and pressure of stellar cores, in stars that lived, died, and scattered their precious, life-giving ashes across the galaxy billions of years ago. Gravity, the great gatherer, then took that enriched dust and gas from the wreckage of those ancient stars and patiently, over eons, pulled it together to form a new star, our sun, and a new planet, our Earth. The very substance of your being is a direct inheritance from the cosmos, a recycled gift from the stars, delivered to this world by the patient, persistent, and creative power of gravity. The same force that choreographs the waltz of galaxies also sculpted the raw materials from which you are made. You are, in the most literal and scientific sense, a child of the cosmos, a temporary and beautiful constellation of ancient stardust, held together for a brief, precious moment of consciousness. And this vessel of stardust, your body, has evolved and learned to thrive within a world that is constantly bathed in the magnetic influence of our star. The sun's magnetic heartbeat, that steady, 11-year rhythm of quiet and storm, has been the background pulse of our planet for 4.5 billion years. The protective shield of Earth's own magnetic field, a guardian born from the same dynamo principles that operate in the sun, has sheltered the long, unbroken chain of life from which you are descended, protecting our atmosphere from being stripped away and creating the stable conditions necessary for evolution's slow, patient, and creative work. You exist in a nested set of magnetic embraces, the field of the Earth, which is your immediate guardian, and the larger, more dynamic field of the heliosphere, which is the broader environment of your planetary home. Every solar flare, every CME, is a ripple in this magnetic pond, a reminder that we are not isolated, but are living within the extended atmosphere of a dynamic and active star. The same nuclear fire that warms our world and powers all of life also sends forth the storms that can, in a very real sense, touch the delicate biological compasses of the creatures with whom we share this planet. In this final recognition, we find a sense of profound belonging. The universe is not a cold, distant, and uncaring machine. It is a deeply interconnected system, a web of gravitational and electromagnetic relationships where every part is in a constant, subtle dialogue with every other part. The force that keeps your feet planted firmly on the ground is the same force that is pulling the Andromeda Galaxy towards us in an inevitable, cosmic embrace. The light that allows you to see the world around you began its journey hundreds of thousands of years ago in a nuclear furnace powered by that same gravity. And the magnetic field that protects you from cosmic radiation is, itself, in a constant, dynamic dance with the magnetic field of the star that gravity built. To be human is to be a living bridge between the vast, impersonal forces of the cosmos and the intimate, personal reality of a single, conscious breath. You are both a spectator and a participant in this grand performance. The universe is not something that is out there separate from you. You are the universe, experiencing itself. And in this gentle, humble recognition of our place in the grand, interconnected scheme of things, we can find not fear, but a sense of peace, a sense of wonder, and a sense of profound and unshakable home. And so, we reach the gentle and final conclusion of our cosmic journey, a quiet drift back from the grand architectures of the cosmos to the serene stillness of this present moment. We have traveled from the sun's turbulent, magnetic heart to Earth's protective magnetosphere, witnessing how these invisible forces shape everything from the shimmering auroras that paint our polar skies to the delicate technological networks that connect our modern lives. The story we've explored tonight, a story of gravity's patient construction and magnetism's dynamic dance, is ultimately one of profound and beautiful interconnectedness. The same magnetic field lines that twist and tangle in the sun's corona reach across 93 million miles of silent, empty space to caress our planet's protective shield, a touch that can be as gentle as a whisper or as powerful as a storm. The charged particles that spiral through the solar wind carry with them the ancient memory of the nuclear furnaces burning in our star's core, delivering the energy that once forged the very atoms that now, for a brief and wondrous time, make up your body. This cosmic relationship between the sun and the earth reveals the elegant and often hidden choreography that governs our universe, a place where seemingly chaotic events like solar flares emerge from the patient, methodical, and predictable processes of magnetic reconnection, and where our own planet's response to these stellar tantrums demonstrates the remarkable resilience of the nested, protective systems that shelter and sustain life. The magnetosphere that surrounds our world isn't simply a static barrier. It is a dynamic, breathing boundary, a living shield that expands and contracts with each solar cycle, that channels cosmic particles into spectacular and harmless light shows, and that has been faithfully protecting our atmosphere and our ancestors for billions of years. Without this magnetic embrace, this gift from our planet's molten heart, our world would likely have suffered the same fate as Mars. Its atmosphere slowly and relentlessly stripped away into space until only a thin, cold, and sterile shell remained. Tonight, as you drift towards the gentle shores of sleep, solar particles are, at this very moment, streaming past our planet at speeds that would carry them from New York to Los Angeles in less than a single, quiet minute. Some of these particles, guided with perfect precision by Earth's magnetic field, are spiraling down toward the polar regions. There, they are colliding with oxygen and nitrogen molecules hundreds of miles above the sleeping surface, creating silent, shimmering curtains of green and red light that dance in the cold, clear Arctic darkness. The indigenous peoples of the far north have watched these same lights for thousands of years, weaving stories of ancestral spirits and celestial guides into the aurora's shifting, ethereal patterns, unknowingly celebrating the very same magnetic processes that we, in our own way, have explored together tonight. The sun's magnetic heartbeat, with its steady, 11-year rhythm of quiet and activity, will continue its ancient pulse long after our own civilization has transformed into something we cannot possibly imagine. Solar maximum will follow solar minimum in in a pattern that began when our star first ignited its nuclear fires. And it will persist until that fuel is finally and peacefully exhausted, billions upon billions of years from now. As you settle deeper into a state of rest, consider that you are part of this magnificent, interconnected system, this cosmic dance between star and planet that has been unfolding for 4.5 billion years. The iron in your blood was forged in the hearts of stars and delivered to this world by the very same cosmic processes that create the space weather we have discussed. The oxygen you are breathing at this moment exists in our atmosphere because our planet's magnetic field protected the fragile, emerging biosphere that first learned to produce it. Every beat of your heart, every gentle rise and fall of your breath, connects you to this vast gravitational and electromagnetic symphony that plays constantly and silently all around you. In the quiet darkness of your room, charged particles are raining down on our atmosphere. Magnetic field lines are reconnecting in ways that would astonish the greatest of physicists. And somewhere, high above the silent, sleeping polar caps, if the conditions are just right, ghostly curtains of light are performing their eternal, silent dance. This is the world that cradles your dreams tonight. A world forged by gravity, protected by magnetism, and warmed by a distant, nuclear fire. A world where the intricate and beautiful dance between chaos and order creates the perfect, gentle conditions for life, for consciousness, and for the peaceful drift towards sleep that now carries you into the final, quiet darkness, where even the sun's magnetic fury becomes just another soft, gentle lullaby in the eternal, cosmic symphony that is your home.